Fibonacci is a mathematician who became famous for his well-known sequence. Do you want to know what that sequence has to do with the golden ratio? Well, pay attention, because you're going to be amazed. Well, let's go there. The Fibonacci sequence starts with 1, and the second number is also a 1, and then what is done to get each number is to add the previous 2. So the third number is a 2, 1 plus 1. The fourth number is a 3, 1 plus 2. The fifth is a 5, 2 plus 3, and so on all the time. Look, here are the first numbers of the famous Fibonacci sequence. If you already knew her, it won't sound weird to you, and if you didn't know her, you'll say, well, wow, and is this so special? What's so special about it? Well, quite a few things. Any integer you can imagine can be put as the sum of distinct Fibonacci numbers. Only one term out of 3 is even. 1 in 4 is a multiple of 3, 1 in 5 is a multiple of 5, and so on all the time. The greatest common divisor of two Fibonacci numbers. It's another Fibonacci number. The infinite sum of the Fibonacci numbers divided by the powers of 10. That is, f sub n divided by 10 raised to n, gives exactly 10 divided by 89. And you know what? 89 is a Fibonacci number. And look how they appear in Pascal's triangle. But probably what has made the Fibonacci sequence most famous is that it appears a lot in nature. And of course no one expected it. In how the branches of the trees are arranged, in how pineapple scales are distributed, how the flowers of the artichoke are formed, the pine cones of the pines or the genealogical tree of the bees. You will like the latter. A drone is the first in the family tree. A 1, he doesn't have a father, but he does have a mother. The queen bee, which is the second generation. 1, 1. The queen has a father and a mother, so the drone has 2 grandparents. The third generation. 1, 1, 2. And the fourth is the drone's 3 great-grandfathers, since the queen's father has no father, poor little bee, and the mother has a father and a mother. 1, 1, 2, 3, and it goes on like this. He has 5 great-great-grandparents. 1, 1, 2, 3, 5, 8 great-great-grandparents. 1, 1, 2, 3, 5, 8, and so on, complying all the time with the Fibonacci sequence. Freaking out, huh? Well, let's go with the other famous thing from this video, the golden ratio. Let's see where that comes from. The ratio or proportion of 2 parts of a segment is said to be golden. It is an old word that means cool, if the ratio of the large part, that is, A, to the small one, that is, B, is equal to the ratio between the total, that is, A plus B, and the large part. A. Okay, but can that be calculated? Yes, we have that a match for B is equal to a plus B match for A. That is, a match for B is equal to 1 plus B match for A. If we call a match for B, phi, because it's cool and on top of that it's a tribute to Phidias, a very famous ancient sculptor who used this. Then phi is equal to 1 plus 1 match for phi. That is, phi squared is equal to phi plus 1. And we are left with one of the equations of all life. Phi squared minus phi plus minus 1 equals 0. If we solve it with that of minus b plus minus square root of b squared minus 4c divided by 2a, we get that phi is equal to 1 plus root of 5 divided by 2. It's the positive solution, which is what we want. Perfect, cool, and what? Okay, what does it matter to us? These 2 famous ones, the Fibonacci sequence, that of adding the previous 2 and the golden ratio, do they have something to do or is it an invention? Well, see if you take 2 consecutive numbers from the Fibonacci sequence and divide them, f2 divided by f1, or then f3 divided by f2, and so, further and further. Fn plus 1 divided by Fn further and further into the limit. That quotient is worth exactly phi, freak out. But in addition, the nth Fibonacci number can be written as a function of phi. Look. The nth Fibonacci number is equal to 1 split by the square root of 5, multiplied by 1 plus the square root of 5 matched by 2 raised to n, minus 1 minus the square root of 5 split by 2 raised to n, that this is equal, you see, to 1 split per the square root of 5, phi raised to n, minus 1 split per phi raised to n. So yes, actually we can almost say that they are two ways of saying the same thing. And then they say that mathematics is not pretty. Do you know how the number pi relates to Don Quixote? Or the Renaissance painter Durer with the magic squares? Subscribe and you will find out about everything.